Welcome again. Today we will study the most awaited difference amplifier. We were waiting for this for a long time, so we will study difference amplifier. So first thing I will do is I will draw the difference amplifier. I request you, do not see my drawing, do it yourself. Remember the trick to how to do it. So draw the op amp, two inputs minus plus. The rule is connect the minus terminal to the output, negative to output, and positive to ground through resistances, negative to output, positive to ground in OPG. Put two more resistances, and then this two will become our input, this will become our output. Let me put everything in a box. Okay, call this VO. Call these two inputs as V1 and V2. Before we proceed with mathematical analysis, let us talk about how to connect this circuit in reality in lab. Okay, so in lab, when you are using this op amp, so I never remember which pin corresponds to which pin that you see in the manual. So for IC 741, I guess this is pin output is pin number 6. These are pin number 2 and 3. Do not ever try to remember those things. Those are unimportant. You can always go to the web nowadays. It's very easy, and just check the pin numbers. That's what I did actually. I mean, and I paused the video and just checked it. It does never. You don't have to remember these things. You can always check these numbers. Okay, so that's not important. What is important is that you also have to connect the two power supplies, whichever pin those are. Check it on the web. So connect them like this. Let me take a source. Say which is plus minus 12 volt or plus minus 15 volt. So I have 12 in series, total 24 volt. So you have to connect it, and then of course this ground you have to connect to this point like this. Okay, so and yeah, I mean, this ground is basically also a reference point. I mean, the point which you take as the ground dot 0 volt, because voltage is of it's a relative value. It's okay. So you connect it like this. Okay, so I have plus minus 12 volt supply. This is the ground, which is taken from the center of these two batteries. Now I have to connect the inputs. Okay, now input in this circuit can be connected in two different ways. Okay, the common way of connecting the inputs are to use two voltage sources. So you can use two voltage sources like this. So connect one voltage source plus minus, the other side at ground. Ground means what? Basically ground means you have to sort all these common grounds. Okay, and take another voltage source and connect it here with V1 plus minus. The other side I can draw like this. Drawing like this means, of course, this has same symbol, so they are actually connected. Drawing is fine, but in the lab you of course have to sort it. Okay, notation wise just drawing this symbol means of course they are connected, but in lab of course you have to connect this. Okay, so this is now, so this in this way, if you use the this difference amplifier in this way, then the output, so you have two voltage sources, V2 and V1. So this is V2, this is V1, this is V2. So then the output you will get is proportional to the difference of these two voltages. Which minus which? This is connected to minus side, so minus V1. This is connected to plus side, plus V2 multiplied by K. This is what you will get. What is this constant K? This depends on this resistances. So normally we need, for a normal ideal difference amplifier, we need this two resistances to be equal. The two that are connected to the inputs, take them R1 and R2. The other two also need to be equal, R2 and R2. Then this K is actually equal to R2 by R1, V2 minus V1. Okay, this is one way you can use it. Now suppose you are you are measuring or amplifying. So this is an amplifier, right? So what is the purpose of an amplifier? Purpose of an amplifier is to amplify some voltage, maybe because you want to measure it. Okay, so to measure, suppose you want to amplify and then measure, because the voltage is very small. Okay, so then suppose you have a network, complicated network. Network means a complicated circuit. Okay, whatever complicated circuit you can think of. So think of a very complicated circuit, as complicated as you can think. Voltage source, current source. I'm drawing blindly something. I do not even. Whatever you can think of, think. Put too many sources. Whatever you would like to do, you do. A very complicated circuit. Okay, and then suppose you want to measure the voltage between these 2 points. So this is a network, a complicated network. So this is a complicated network, and call this point A and point B. Okay, and you want to measure this voltage. How will you do it? What you have to do is that you have to so this is a complicated network and this is the amplifier. Now I have to connect this to the input of the amplifier. Okay, so this is the amplifier part. So what you can do, you can just connect this one terminal here and the other terminal here. Okay, so then VO will be equal to R2 by R1 multiplied by V2 minus V1. Now V2 is VA. Okay, so VA minus VB. This is VA, this is at VB. So this is what you will get at this point. Okay, now suppose you want to measure it, then what you have to do? Then you take an voltmeter. Okay, so this voltage you connect here. This is a voltmeter, but you have to close the circuit. So what you can do? You connect this to the ground. Okay, now so you can use it in this way. Fine. You can also use it in this way. Suppose you have a network and between these two terminals you want to measure the voltage after amplification, you can use it in this way. Now if you want, you can do another thing. So see, these two circuits, this network and the amplifier, they do not have a common ground. Okay, so if you want to have a common ground, you can connect any point of this circuit, whichever you want to take as the reference, to this ground. This is the ground line, right? This is the ground line. So any point in this circuit, you can, in theory, whichever you like to consider as the reference, you can connect to this ground, any point in theory. So, or even one of these points. So suppose you want to make VB as your reference, so then this is VB, so you can connect this to the ground. Now they will have common ground. Now this particular circuit, this particular amplifier will not need this common ground. That's the nice thing about this this amplifier. Okay, so this this common ground, so this red line is optional. It will work even without this red line, this common ground connection. Okay, so it will work even without the common ground. That is the red line. Okay, so which means if I if I can, instead of having two sources, I can also take only one source and use it in this way. Okay, and call this VD. Okay, then so there you need not connect this is not required, so you need not connect this ground to this. Okay, so then once again the output will be VO will be equal to minus R2 by R1. I mean then this is plus side, this is minus side. Okay, so VD therefore we'll have this minus VD. Because the plus side of VD is connected to the minus side. Okay, or if you do not like this minus side, then let me take this reference in the opposite direction, then plus is to plus, minus is to minus, then it's plus. Okay, so this is also a valid circuit. You can use it in this way, and you can also use it with a common ground. Like this. So you may choose to say connect it like this, or you may like to choose connect it to this. Either is okay. So either is okay. So this is also a correct circuit. Okay. So so basically the point here is this difference amplifier can be used in mainly two different ways. One with a common ground, another without a common ground. So this is with common ground. So you can connect it here, you can also connect it here, okay, and which also means that suppose I have two sources here in series, plus minus, if I have two sources, call it VD1 and VD2, or maybe 2 and 1, sorry, 1 and 2, 1 side 2. Okay. You can also connect this red line in between here. Red. This is also fine. This will also work. So this red, this common ground, you can connect here, you can connect here, you can connect here. This will work. And here there is no common ground. So this is without common ground. Now you just observe a small thing is that this particular circuit, okay, give it a name, circuit 1, this circuit and this circuit are same. Convince yourself, these are similar circuits. So if you replace VD1 with V1 and so let me show you together. If you replace VD1 with V1, VD2 with V2, then these two circuits are similar. Okay, so this is similar to circuit 1. Okay, so the point is essentially you can or cannot have, may or may not have this common ground. Here we have, here we do not. Okay, so this particular circuit can be used even without common ground, but essential point is that in general later on also we will see some circuits where common ground between the circuit which we are probing, that means like this network circuit that on which we are doing the measurement, and the amplifier in general may need a common ground between them. This particular this amplifier doesn't need it. Even if you put the common ground, no problem, no harm is there. So it's maybe in general a safe trick to always have a common ground. Okay, so this can be used in two different ways, and I have shown you detailed connection with power supply, etc., everything. Okay, now next, so the remaining in the remaining part of this class, we will do a thorough analysis of this difference amplifier with graphical method, the method we have studied so far. একটু পজ করছি। Okay, so now we are going to analyze of difference amplifier So let us take this circuit first without the common ground. Okay. Now, once again, the question is, what is the question? Given Vd, that is the input, given Vd, what will be the output? Vo. Okay. Okay. So Vo is the unknown. Now, so this is what? This is Vp. This is Vn. Now unknowns are, of course, output Vd, but we do not know Vp, Vn, either of them. So we have Vp as well as Vn. So we have three unknowns. We can find three equations, three relations between them. But the problem, difficulty we will have is that we cannot draw a 3D picture, 3D graph. So it's difficult. So what the trick that I will use, I will write the Vn as Vp minus Vd. You see, this is okay. So what we will do, we will, no, not this, I mean we will write, we'll find some relation between Vp and Vn from this part of the circuit. Okay. So what can be that relationship? So you see that the current here is 0 in this branch. Okay, here no current can go into the op amp, so this is crossed. Similarly, no current can go here, I mean into or out of the op amp. Okay, so there is no current there. So therefore the current must flow, if any current flows, it will flow like this, like this. Okay, from here it will completely flow in this path or in the opposite path. Okay, it cannot get into the op amp. Okay, so let me take this current in this direction, starting from here in okay. So this is the way the current flows. Okay, and if you want to continue this line further, this will flow like this. So out of the op amp, it starts from here and it goes like this and it goes to the ground. Starts from the op amp and it goes to the ground. Okay, and if you ask, okay, how is the circuit closed, you see that this ground, uh, once it goes to the ground, it basically is connected to this point, and then these 2 points are connected here. This way you can also think about the conservation of charge if you are really that much keen about it. But this is the path of the current we are going to consider. This current, let me call it I. Okay, but if we can write the two unknowns as VO is 1, of course this is output, another VP minus VN. Okay, so if we write these two as two variables, two unknowns, then with a 2D graph we can solve it. Okay, so let us find the relationships between these quantities. Okay, so relations or equations. So first let's consider this part of the circuit. Okay, this part of the circuit. Once so you know that the current, if there is any current that will not flow in this branch here, it will not flow even in this branch, because no current can go in or out through the input terminals of an op amp. So current can only flow like this, starting from here it goes like this and to the ground. Okay, so this is the way the current will flow, like this. Okay. And no current can flow here or here. So therefore this current is I. So let's write how much is I. I is nothing but, or let's start like this. So this point is at potential VO here. So we can write VO minus the drop R2I plus R1I. So I R2 plus R1. So this is the potential here. Then a potential rise. So plus Vd. Then another drop R1I R2I. So minus I R1 plus R2. This will be equal to 0, the potential at this point. Okay. So from this we can write that VO plus Vd is equal to, let us take these two terms on the other side, we will have 2I R1 plus R2. From this you can also write that I is equal to VO plus Vd divided by 2 R1 plus R2. Okay. Then what can we say about the potential difference between these 2 points, Vp and Vn? We can write Vn, which is the potential at this point, is equal, then okay, minus this drop, minus I R1, then potential rise, so plus Vd minus I R1. So this will be equal to Vp. Okay. So therefore from this we can write Vn, or okay, let me take Vn to the right side, then we can write Vp minus Vn. So, I am bringing this here. So, then I will have Vp minus Vn. This is equal to nothing but minus I, this is R1, minus IR1 minus IR1. So, minus 2 IR1 plus Vd. From this we can write Vp minus Vn is equal to minus 2 R1. I is how much? I is this. So, in place of I we write Vo plus Vd by 2 R1 plus R2, okay, and then plus Vd. Now, this 2 and this 2 you can cancel, therefore, this will be equal to Vo R1 by this term, Vo R1 by R1 plus R2, and then okay, with a minus sign, and please check my calculation always, I may do small mistakes, okay. Then minus Vd R1 by this and a Vd. So, let me take this Vd common, okay. So, then I have plus 1 minus this term R1 by R1 plus R2, R1 by R1 plus R2. Okay. So, then this is equal to minus Vo R1 by R1 plus R2, and here it will be R1 plus R2 minus R1. So, R2, so plus Vd R2 by R1 plus R2. Okay. So, this is Vp minus Vn. Now, from this let us reorganize the terms a bit. Okay. So, this is Vp minus Vn. Let us multiply R1 plus R2 everywhere, here, here, here. So, then we will have Vp minus Vn R1 plus R2. This will be equal to minus Vo R1, okay, and plus Vd R2. Now, let me bring this plus Vd R2 this side. So, it will be Vd minus Vd R2 here. Let me do a small step jump. Let me divide by R1 all the terms. So, divide by R1, divide by R1. And okay, let me multiply with a minus 1. So, this becomes plus, this becomes plus, this becomes minus. Correct? I guess so. So, Vo is equal to Vp minus Vn times this factor plus Vd times this factor. Okay. I guess I haven't made any mistake. Okay. Okay. So, this is relation 1. Okay. And the other relation between this Vp minus Vn and Vo, so these two variables, comes from the static characteristic. Okay. So, let us now draw these two relationships on a common graph. So, x axis is Vp minus Vn, y axis is the output Vo. Now, the static characteristic looks like this. Okay. And so, this is one relationship. Another relationship comes from this. Okay. Here this term is the y axis, y value, this is the x value. So, this is x, right. x coordinate, this is the x coordinate. So, you see y is equal to minus mx plus something, minus mx plus something. So, how will the curve look like? It will be a straight line with negative slope and the intercept will be positive. So, it will be a line like this. Okay. So, the intercept is positive because this value is positive, assuming Vd is positive. Okay. Resistances are of course positive, and then slope is negative because of this minus sign. Let me highlight this. This is, there is a minus sign here. Okay. Okay. So, this will be the solution therefore, and so the what is the solution then? So, the solution, so at this solution you see that the x axis, the value of x, that is Vp minus Vn, is 0, ideally 0, because ideally this part should be almost vertical. So, we can write Vp minus Vn is almost equal to 0. Okay. And what is the y value? Vo. Now, Vo, let us take this equation and put the value of Vp minus Vn equal to 0. So, from this equation then we can write Vo is equal to, this part is 0, therefore, we have Vd R2 by R1. Okay. So, it is simple, right. So, the output will be Vd multiplied by R2 by R1. So, the analysis is now quite straightforward. We have done so many similar things, so many practice, it's now should be very simple. But what comment can we make from this? So, see, the output is proportional to Vd. What is Vd? Vd is nothing but this voltage, which is nothing but V2 minus V1, V2 minus V1. So, the output is proportional to the difference of these two voltages. So, you can connect a voltage in this differential form like this. Okay. So, and the output will be therefore proportional to this Vd. Okay. Now, is the okay, and how many solutions can we have? We can have only one solution, because there is only one intersection. You can now change the value of, say, the position of this green curve. This green curve comes from this relationship where you can change the value of Vd, do not change any resistance, only change the input. Then the slope of this equation will remain same, but the intercept will become more or less. So, if we increase Vd, this curve goes up, and after some point you see it will be like this. So, the solution will be here. So, output will not increase further. Okay. So, that is the saturation region. But if you decrease Vd, it goes down, 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 and here, and after this point again a saturation will occur if you bring Vd further down. Normally it is, I keep it here for some value of Vd which is positive. Okay. And what else can we say? Okay. So, then if Vd is within the limit of saturation, then Vp minus Vn is equal to 0, right. If it goes beyond saturation, then Vp minus Vn will be this much. So, that will not be 0, but within the limit of saturation, this is almost equal to 0. So, we can say that virtual sorting is working, is true. So, comments or observations, virtual sorting between Vp and Vn is true. Okay, what else? The solution you can test, the solution point will be a stable point. Stable solution, you can test it yourself like the way we did in the previous class. And output is proportional to the difference between V1 and V2, because Vd is V2 minus V1. So, we can write this is basic, this is the, I can write this is point number 0. Okay. So, output is proportional to V2 minus V1. So, this works as a difference amplifier, an amplifier which amplifies the difference between two voltages. So, this is how it works. Okay. Anything else? I think this is okay, fine, that is fine. Okay. So, now if you have understood this much, it will be great. Next, we will see briefly the situation where we have a common ground. So, previously we have said that we can use this difference amplifier in two different modes without common ground. Okay. So, and here with a common ground. Okay. So, the analysis that we have done is for the case without common ground. Now, how will it be if we have a common ground? So, let me just copy this circuit. Okay. And now, I reconnect this circuit with a common ground and two voltage sources you can think of. Okay. So, let us connect two voltage sources in series. Okay. Call this plus minus, this is V2. So, this value is V2. So, I can write V2 here, and this value. So, let me call this so plus minus they are in series addition, and from this middle point I take the common ground. Okay. So, this is with common ground, and okay, let me write V2 here only. So, the potential at this point is V2. Let me call this as, you can call this as VD2 if you want, and you can call this as VD1, right. And this point is, so the absolute potential here is V1, and this is the difference between these two terminals. Also, this is the difference between these two terminals. Okay. So, the source has a value of VD1, this source has an EMF of VD2. The absolute potential here is denoted with V1, the absolute potential at this point is denoted with V2. We have a common ground here. So, this potential is 0 volt. Okay. Now, we have to do the analysis for this circuit. So, what do you have to do? We have to find the answer given input voltages VD1, VD2, that means V1, V2, what will be the value of the output? This is the basic question we always ask. Given the inputs, what will be the output? Okay. And Now to begin with, so this point is at 0 potential, so that means this point is at a potential Vd2. So V2 will be equal to Vd2. This is 0, 0 plus Vd2 is V2. Okay. So if this is V2, now current can flow like this, okay, but no current can go in this branch through the op amp's input terminal. So the current goes only like this. This point is at V2, this point is at 0 volt. So what will be the potential here? Vp, how much? Potential divider rule. Vp will be nothing but equal to V2 divided by this R1 plus R2. This is nothing but this current, this multiplied by R2. This will be the value of Vp. Okay. So this part is the current here. This multiplied by this resistance is this voltage drop. So this becomes Vp. Okay. So we know Vp. Okay. This is one thing. Now what can we say about Vn? Okay. Now before that, okay, what can we say about V1? V1 is nothing but equal to minus Vd1, because this side is plus, this side is minus, so this is plus minus. So there, and this, so starting from 0, I have a potential drop. So V1 is minus Vd1. Okay. So that means given V2, given Vd2, V2 can be computed directly. Similarly, given Vd1, V1 can be computed directly. So these are inputs. So this is one input, this is another input, these two are given. Given. Vp is found like this. Now Vn. Okay. Vn is how much? So let's see that there is no current here, right? No current at this point. This point is at value VO. So current can flow only like this. Nothing can get bypassed here. This is at VO, this is at V1. So another potential divider rule will give me the value of Vn here. So let me write the value directly. Vn will be VO multiplied by R1 divided by R1 plus R2. This is R2, and plus V1 multiplied by R2 by R1 plus R2. Okay. So you can find it by finding the value of this current. Okay. Now let me write this in this way. Output VO, this will be equal to Vn multiplied by R1 plus R2 divided by R1, okay, and then minus V1 R2 by R1. Okay. So you just you just manipulate this equation to get this. Okay. Vn times this by R1 minus V1 R2 by R1. Okay. So this is another equation that we have. And the third relationship is the static characteristic. So now let's use all of them together and find the solution. Vp minus Vn, Vo. Okay. Now the static characteristic is of course like this. and here you observe that the value of Vn, sorry, no, not this one, value of Vp is known in terms of the input. Okay, so let me write this as Vp is equal to V2 multiplied by R2 by R1 plus R2 minus Vn, correct, R2 by R1 plus R2, R2 by R1 plus R2. This is the x-axis. Now, from this, we draw another graph which is just opposite to this. So, let this be x-axis, which is now will be equal to Vn minus this V2 by V2 R2 by R1 plus R2. Okay, so this will be opposite. Okay, and now from this we draw another graph where the x-axis will be Vn only. Okay, so from this we draw another graph Vn where this curve will get shifted, and this point is the point where this quantity is equal to 0. So, Vn is equal to this much. So, at this point Vn is equal to this value V2 R2 by R1 plus R2. So, you observe that if we change the value of V2, the input V2, this curve will move towards the left or right. Okay. So, this is one curve. Now, the other curve we will get from this VO equal to Vn multiplied by this minus this. So, this is y equal to mx minus c, y equal to mx minus c. So, that will look like a straight line with positive slope and negative intercept like this. Okay. So, this is from relation or equation 2, which is here. Okay. So, what will be the solution? The solution is this. So, this is the solution, right. And now, what can you say about the solution? For an ideal op amp, this is almost a vertical line. Therefore, we can write Vn is this much. Okay. So, solution, at the solution Vn x-axis is this much, Vn is equal to V2 R2 by R1 plus R2, and the y value, that is VO, that we can get by putting the value of Vn in this equation. Okay. So, here in place of Vn we put this value. So, we write V2 R2 divided by R1 plus R2, right. This value we have put in place of Vn. Now this goes away, so we are left with V2 R2 by R1 minus V1 R2 by R1. So V2 minus V1, we can take it common, R2 by R1. So this is output VO. Okay, so this is the answer. Okay, it's easy. Okay, now okay, great. So I just give you some small task without doing it myself. Okay, you show this thing yourselves. Okay, so check that virtual sorting is working, is true. Then the solution point is stable. Check it. Okay, do it, try it yourself, and if you need any help, you can ask us in the forum. What else? Okay, the obvious thing is that the output is proportional to the difference between two inputs. So that means this is a difference amplifier which amplifies the difference of two voltages, two inputs V2 and V1, which are applied like this, one here V1, another here V2. Okay, so that is I guess simple. Another small exercise that you do yourself, okay, is that analyze in this graph how will the solution change if you change either of the two inputs V1 or V2. So if you change V1, that means VD1, or V2, that means VD2. If you change either of these two inputs, how will these two graphs will change? Okay, so just think of it yourself. I am just giving you a small clue. So this graph, you see, this crossover point depends on the value of V2. Okay, therefore this graph will change its crossover point depending on the value of V2, like this. Say if you increase V2 and if V2 is positive, then this curve will move like this. And if you decrease if you increase it further, then at some point saturation will take place. Similarly, if you decrease V2, this comes to the left side, and then so at this point the output is negative, because if you are decreasing V2, okay, because the output is proportional to V2 minus V1. So if you decrease V2, you know output is going to become negative at some point. So here the output is negative. You bring it further down, then saturation takes place. Okay, so output doesn't go down any further. And for a normal positive value of V2, I keep it here. Similarly, if you now change V1, this curve is not going to change, but this curve is going to change. Why? Because this depends. So this is from relation number 2, this equation, relation 2. So if you change V1, the slope will remain same, but the y-intercept will go up or down. So if you say, for example, increase V1, then if you increase V1, then this curve goes down, and then at some point the output becomes negative. If you bring it further down, then saturation takes place. If you decrease V1, it goes up, up, then it becomes positive, and then if you bring it further up, then once again saturation takes place. And let me just keep it here for a normal positive value of okay. So here here the y-intercept is negative, so that means V1 is positive. Okay. Thank you.